Hello and welcome to another lecture from my class, PSYC 440/640. The class is called Experimental Methods, but is really more a class on univariate data analytic techniques from a model comparisons perspective, at least for the most part. As usual, I'm starting with a comic from the excellent web comic series PhDcomics.com. This is a classic, or at least one that I remember from around the time that I got my PhD. It felt like a huge step for me, although maybe in the big scheme of things it wasn't that big a deal. But I felt proud, and hopefully you feel proud too. And if you're wondering, this little note here at the bottom about starting SPSS on your computer is just a reminder that if you're enrolled in my class and you have access to the data sets I'm going to talk about, you can go ahead and fire up SPSS right now and you can kind of play along with the analyses that I present. Anyway, this class is called More About Multiple Regression. Not the most inspired title for a lecture, but we are just continuing to talk about multiple regression, trying to introduce some new topics under that heading. Today I want to talk about the idea of building models, that is adding predictor variables to a model using an example, one that's from the textbook, Andy Field's Discovering Statistics Using SPSS. In order to talk about multiple regression, though, I need to talk a little bit about partial and semi-partial correlations, or really more about the idea that underlies both of those, the idea of shared variance. Now, this is a topic that actually comes in a way from an earlier chapter in the textbook and really could have been folded into an earlier lecture on correlations, but I kind of deliberately held off because I think it makes more sense to introduce it in the context of multiple regression. And with that in mind, then, after talking a little bit about partial and semi-partial correlations, I'm just going to do another example of multiple regression and talk a little bit about the different methods that SPSS and other stats programs offer for running regression analyses. And I'll even highlight a couple of the problems that can come up when we misunderstand or misuse some of these methods. Okay, so multiple regression, just a regression that has two or more predictor variables. In the case of a multiple regression with just two predictor variables, it's fairly easy to visualize what this regression model looks like geometrically. We can imagine a y-axis for our outcome variable and then two x-axes for our two predictor variables, kind of defining a three-dimensional space. All our data are a cloud of dots that kind of hover or float in that three-dimensional space, and our model is a flat plane that kind of slices down through that cloud of dots. And we can describe that plane in terms of its y-intercept, that is where it slices through the y-axis, and also in terms of the slopes of each of the two major edges. I mean, edges is a bit of a misnomer though, because really the plane extends infinitely, but you could describe sort of the slope in one direction and the slope in the other direction, and that would be a way of representing geometrically the model. Now, this gets a lot harder to do when we have more than two predictor variables, unless you have some amazing ability to think in high dimensional space. But in principle, the algebra and the process that we go through when we run a regression analysis, a multiple regression analysis that is, remains largely the same. So by way of an example, I'm going to use some data and kind of an example that comes from our textbook, Andy Field's Discovering Statistics Using SPSS. And here, imagine that you're an educational psychologist or a school psychologist and you're interested in studying exam performance, and particularly in studying the effects that exam anxiety has on exam performance. You know, the extent to which people feel anxious when approaching a test. What, if any, effect does that have on actual performance on those tests? So if we wanted to represent this pictographically, we'd have a predictor and outcome variables like so, and we're looking at the relationship between the two. And it might occur to us that there are some potential confounding variables out there, some variables that might influence in some way the relationship between the predictor and the outcome variable. One potential confound would be time spent revising. Now, revising is just a British word for studying, and the Field textbook is British, or Field himself is English, so I guess that's where that word comes from. But essentially, time spent studying. And the idea here is that time spent studying hopefully has some influence on exam performance, and or some relationship with exam performance, and maybe it has some relationship with exam anxiety. It is out there. It's a potential confound, in so much as it can influence our understanding of the relationship between our main predictor and outcome variable. So what do we do about that? Well, we take our potential confound and we move it in to our model. We add it in as a predictor variable. This is a way of exerting statistical control over this confound. So the expectation here is that you're able to measure in your sample of people time spent studying. You ask people to self-report their level of anxiety, you ask people to self-report their grades, and then you ask people to self-report the amount of time that they're studying, and you use that potential confound, time spent studying, time spent revising, as a predictor variable in your model. You can now try to describe its relationship to exam performance, and you can also try to describe the relationship between exam anxiety and exam performance while holding constant any effect or influence from time spent studying. That's sort of the gist of statistical control. Now, I'll say really briefly, you could try to do some sort of methodological control for this variable. For instance, you could try to recruit people who all into your studies, into your sample, who all study exactly the same amount of time. Or you could try to experimentally control this confound by recruiting people into the sample and then somehow enforcing a standard amount of studying, like everyone is allowed to study or really must study exactly 4 hours for this upcoming exam. So either way, you're trying to hold that variable exam time spent studying constant at some value. That would probably be pretty hard to do because studying is something that people largely do on their own. So you might say, well, we can't kind of methodologically or experimentally control this variable. Instead, we're going to allow it to vary, as it most certainly does in the real world, and we're instead going to measure it and include it in our calculations, and thus have statistical control. Now, I should also say at this point that the choice of adding a variable to the model, that is adding time spent studying to a model which you initially were thinking of to describe the relationship between exam anxiety and performance, the choice of adding new predictor variables, reaching for more and more statistical control, should be done based on theory and based on previous research. With powerful computing, such as the computing that we have on almost any laptop or desktop computer these days, you can, in principle, add lots and lots and lots of predictor variables to your models. There are all sorts of reasons why that's probably not such a good idea, and I'll talk about some of them a little bit later in this very lecture. But for the time being, just note that if we were, in this example, going to add in time spent studying, then hopefully that's based on some good theoretical understanding of how that variable influences our predictor and outcome. That's not hard to imagine how it could. Or some sort of clinical or observational evidence to suggest that this is an important variable. Based on your experience and your knowledge of the literature as an educational psychologist, it makes abundant sense to include time spent studying as a variable in your model, and thus have the ability to understand its relationship with the outcome variable and the ability to use statistical control when talking about the relationship between exam anxiety and the outcome variable. Again, you do it based on theory and sort of clinical experience, not just sort of willy-nilly picking predictor variables and adding them into the model. Another thing we need to think about, and really why this is so important, is when we add predictor variables to the model, or essentially when we have more than one predictor variable to the model, we don't just have to think about the relationship between those predictor variables and the outcome variable, but we also have to start thinking about the relationships between those predictor variables, the extent to which those predictor variables, in this case exam anxiety and time spent revising, how much they're correlated with each other. And that can get kind of complicated. The extent to which those variables are or are not correlated with each other will have some influence on how we make and how we interpret a model that includes both of them. Now, in order to talk about this idea of variables which are correlated with each other, variables which sort of overlap or share variance, it's important now, or it's, I guess, appropriate now to talk about partial and semi-partial correlation. And I can't help but include this other comic from the webcomic series xkcd.com presenting a Venn diagram, which I think is very funny. Okay. Now I'll define partial and semi-partial correlation in just a few more slides, but before I do that, I want to introduce an example. It's one that comes from our textbook, Andy Field's Discovering Statistics Using SPSS. And if you are in my class, you can have access to this data set through Blackboard. If you're not, I'm almost certain you can go to the publisher's website for the book and find the data sets there. I don't think you have to purchase the text to gain access to those data sets. Anyway, the data set is called Exam Anxiety, and it concerns or includes data for time spent revising, that is studying, exam performance on a percentage scale, and exam anxiety measured on some scale for that construct. Now, we're already familiar with the idea of coefficient of determination, or R squared, as a way of expressing the variance that's shared between two variables. So for instance, we could just do the simple correlations between time spent studying, anxiety, and performance, and then we could square each of those values to get a sense of the variance that's shared between the pairs of variables. How much variance is shared between time spent studying and exam performance, or time spent studying and anxiety. But what's new or interesting at this point is the idea that not all variance that's shared between two variables is unique to their relationship. Some variance is shared with other variables. That is, some amount of the overlap between exam anxiety and exam performance is not just about those two variables, but also includes another variable, or potentially many other variables. In this case, we're just focusing on time spent studying. And I earlier presented a Venn diagram, kind of a web cartoon comic for a Venn diagram, but Venn diagrams actually make sense here, or at least we try to use them sometime to express with area of overlap the kind of relationship between unique and shared variance between different variables. So for instance, we can look at the overlap between exam performance and time spent studying, and it's about 15.7%. And then there's a certain amount of overlap between exam performance and exam anxiety, and it's 19 and some percent. And then there's a certain amount of overlap between exam anxiety and time spent studying, and that's a certain amount of percent that actually I can't picture on this page because I sort of ran out of space. If we put it all together, we can see that some of the variance variance that's shared between two variables, for instance exam performance and time spent studying, is sort of unique to their relationship, but some of it is also associated with another variable, in this case exam anxiety. There's that sort of diagonally slashed areas in this image to show the unique variance between our predictor variables and our outcome variable, and then there's this sort of checkered pattern area to suggest the non-unique or the shared variance that is not unique to either of those two paired relationships. Now, Venn diagrams can be kind of useful for visualizing this, but ultimately they can become a little bit unwieldy to use. And in any case, we almost always want to do numerical calculations. And one of the ways we can do one of these numerical calculations is by looking at partial correlation. That's just the relationship between two variables, in this case, exam performance and exam anxiety, after or controlling for the effect the third variable has on both of them. So if we can remove the effect of time spent studying on anxiety and time spent studying on performance, what's the remaining relationship between anxiety and performance? That's the partial correlation. When we talk about partial correlations, we often say things like they're the correlation between anxiety and performance with time spent studying partialed out of both. And that's key here, because the idea is we're removing that effect of time spent studying on both performance and on anxiety. And I've included here the formula for partial correlation, not so much because I think it's important to memorize this formula. It's not that hard to use. I mean, you could do one of these by hand, but it's almost certainly the case that you're going to be using SPSS or Excel or even a scientific calculator to do the calculation for you. The reason I included the formula right now is just to kind of show you in the numerator how we're taking that correlation between anxiety and performance and we're subtracting out, quite literally, elements of the correlation between anxiety and revision and performance and revision. Anyway, like I said, you probably won't be doing these by hand. You'll probably be using SPSS or some other statistics program. If you're using SPSS, especially if you're following along right now, you can open up your data set and you can use analyze, correlate, partial, because of course we're doing partial correlations. And in the field for variables in our partial correlations workspace, you include our predictor and outcome variable that we're principally interested in, that is exam performance and exam anxiety. And then in our controlling for box, that's where you put the variable you're trying to partial out. In this case, it's time spent studying. The test for significance, the default is probably a two-tailed test. And if you want, you can click on options and ask for zero order correlations as well. You don't have to do that, but you might want to. You can also, as you can see there, ask for means and standard deviations if that's interesting. When I was making the PowerPoint, I didn't because it just didn't seem all that important for this example. Anyway, once you've done all that, you can hit continue and then hit OK. And you'll get a bit of output. Here's my output right here. And the part to focus on right now is at least the part towards the bottom where we're looking at the relationship between exam performance and exam anxiety after controlling for time spent studying. And so we can say, well, the partial correlation between performance and anxiety is about -2 or 0.25. That's after we've partialed out time spent studying. We've taken it out of the picture, and this is useful. Sometimes when you're playing around with a data set, when you're trying to understand relationships between variables, it's valuable to partial out different variables and look at relationships. By the way, if you asked for zero order correlations, that's the part of the table towards the top where there is no control variable. Those are just regular bivariate correlations, Pearson correlations, as you can see from the little footnote there. So partial correlations are one type of calculation we might do when we have more than two variables and there are patterns of overlapping shared variance between pairs of those variables. Another type of calculation are semi-partial correlations, or somewhat confusingly sometimes called part correlations. Anyway, semi-partial correlations give us the relationship between two variables after controlling for the effect that a third variable has on only one of them, not on both of them, as was the case in partial correlations. So we might ask, what's the relationship between anxiety and performance with the effect of revising or studying partialed out of anxiety only? If we're doing that, if we're interested in answering that question, we'd compute a semi-partial correlation. And in SPSS, how you do that is go to Analyze Regression, because you have to use the regression module, linear regression. Our outcome variable is the variable anxiety, and our predictor variables are going to be, or independent variables are going to be time spent studying and exam performance. Because we want to partial out the effect of time spent studying on anxiety and then look at the relationship between anxiety and performance after that effect of time spent studying has been partialed out of anxiety. It just happens to be the way we've set up this example. Now, while working in the module, make sure you click on the statistics button and ask for part and partial correlations. As you can see, I have there. You don't need the other checked boxes. I think they're just defaults. Hit continue, hit OK, and you'll get a bit of regression output. The part to focus on is the table for coefficients, where you'll see, if you asked for it, an additional portion of the table that gives you the part and partial correlations. Here you can see if we look at the relationship between exam performance and exam anxiety, if we look at the part correlation, that's the correlation after the effect of time spent studying has been partialed out of or pulled out of exam anxiety. By the way, you can also see the partial correlation, which is the same value we saw as before when we did calculations of partial correlation. And there's also the zero order correlation. That's just the regular old bivariate correlation between exam performance and exam anxiety. Now, semi-partial correlations are useful for examining the relationship between a predictor and an outcome variable after a third variable that has already contributed to the outcome variable. That is, after we've already taken into account the effect that a third variable has on that outcome variable. And that idea of looking at relationships after other relationships have been taken into account is kind of the heart and soul of multiple regression analysis, or at least the way we often do multiple regression analysis in psychology. And with that in mind, let's move on and talk a little bit about multiple regression. Now, SPSS offers some different options for how to run multiple regressions, and these options are similar to those you'd find in other stats programs. There are different choices, and I like to kind of organize them into two broad categories. The first is researcher-driven approaches, that is, approaches where the researcher, you know, the data analyst, makes decisions about which variables go into the model, which order they go into the model, and so on. And then there are some other options which are computer-driven or program-driven options where SPSS is making the call as to which variables go into or stay in the model. Now let's focus first on the researcher-driven options. The first is just simply called forced entry. That's where all predictor variables enter the model at the same time. And by enter the model, what I mean is they are all added to an augmented model at the same time. You might have a compact model which has no predictor variables in it, and then your augmented model that has the two predictor variables in it, or however many you have. Those go in one step. In SPSS, this is called enter, or at least that's the name of the option that you select in the regression module. So if we're working with our example here from Andy Field's textbook, we're still in the regression module, so analyze regression linear. The only thing we're changing is, actually we're not changing anything, because the default for method, you can see kind of in the center with the pull down, is enter. If it's not enter, then just adjust the pull down menu so that is set for enter. We have our one outcome variable is exam performance, and then we've got our two predictor variables, time spent studying and anxiety. Those go into block 1 of 1. A block is just a group of predictor variables that are added to a model at the same time. We're adding these variables at the same time because we're doing a kind of a forced entry, so they have to both go in the same block. Go ahead and click on the statistics button, and then you can select model fit and R-squared change. I'll talk about that in a little bit. Estimates for regression coefficients is probably default checked, but you might want to check on confidence intervals so you get confidence intervals for those regression coefficients. Once you've done that, hit continue, hit OK, and you'll get some output. Now your output looks a little bit like this. Right up near the top there's going to be a model summary. There's only one model here, and technically there are two models because there's a compact model that has no predictor variables in it, but the one model that's referred to here is the one and only one augmented model that includes our two predictor variables, anxiety and time spent studying. And we can see here that if we look at R-squared, we're explaining about 21% of the variance in exam performance by using the predictor variables exam anxiety and time spent studying. If we use adjusted R-squared to kind of estimate what the effect size in the population is, it's probably more like 19%, but that's pretty close. You can see that this is significant. The significant F change at the far right of this table, that's just expressing the significance test for the comparison between this augmented model and a compact model that has no predictor variables in it. I didn't include the ANOVA table that you get from the output, but it will essentially recapitulate this these analyses, so it's kind of redundant. It's basically saying these predictor variables in combination are significantly better at describing the data than a model which includes no predictor variables. If we slide down to the bottom, you can see your table for your regression coefficients, the unstandardized regression coefficients that you might use if you were to write out the model, also the standardized regression coefficients and their t-tests and significance levels, and if you asked for them, the confidence intervals for those unstandardized regression coefficients. A related way of doing multiple regression analysis is hierarchical, or sometimes called blockwise entry. This is basically like forced entry, except you're breaking up the predictor variables into separate blocks, and they're blocks that you choose in an order that you choose. So the researcher, that's you, the data analyst, determines the order that the predictor variables are entered into the model. We're still using the SPSS option for enter. We're just now putting those predictor variables in separate blocks. So if you're going back, or if you go back to your regression module, just analyze regression linear, now we're going to put those two predictor variables, time spent studying and exam anxiety, into two separate blocks. I'm going to begin with time spent studying, and then I will, in block 1 of 1, then I'll click the next button, which will give me block 2 of 2, and I'll enter my other predictor variable, exam anxiety, at that point. Now right away you can see that there are essentially two orders in which I could enter these two predictor variables. The first order would be something like anxiety in my step 1 or block 1, and time spent studying in step 2. And it's important to note here that in step 2 of model building, anxiety, which was entered at step 1, stays in the model. So that's the first order, or at least one of the two possible orders. And the other is just the reverse. It would be an order in which revising, time spent studying, enters at step 1, and then it stays in the model, and at step 2, exam anxiety goes into the model. So here's some output from that first order that I described, where we're entering exam anxiety first and then time spent studying. If you look up at the top at the model summary, you can see that an augmented model, that's model number 1, that's an augmented model that includes only exam anxiety, explains about 19% of the variance in the outcome variable, and is significantly different from the compact model that includes no predictor variables. You can see model 2, that's the second augmented model, where we're adding now time spent studying into the augmented model, and we can see here that that model explains about maybe 20% of the variance in the outcome variable. If you look for at the column for R-squared change, you can see that difference. It's about 1% of the variance improvement, and you can also see, if you slide over to the significance for that change, that that is not a significant improvement in fit. So in the model summary, we compare for model 1, we compare the first augmented model to the compact model, but model 2 is compared to the second augmented model is compared to the first augmented model, and this gives us a sense of kind of the incremental improvement in fit that we get for adding each additional predictor variable. Simply put, adding time spent studying doesn't really improve the fit of the model very much. It does a little, about 1% of additional variance explained, but that's not statistically significant. That's not enough of an improvement given the additional complexity of the model. We're adding an extra parameter estimate to the model. Anyway, if you slide down, you can see the table for the coefficients, and you can look at the t-tests for each of those regression coefficients, and you can notice that exam anxiety is significant in both augmented models. So if you look at the value for the unstandardized and standardized regression coefficients, and then look at the t-tests and significance levels, you can see that anxiety contributes in both models. You can also note that time spent studying is not a significant contributor in the second augmented model. So that value for the the value for the regression coefficient is relatively small. You can see the t-test associated with it is relatively small. That's just testing whether that slope 0.241 is significantly different from a slope of 0, and in this test it is not. So you might conclude that time spent studying isn't really a significant predictor in that second augmented model. Now here's the analysis basically when I ran the orders in the other order, that is entering time spent studying first in step 1 and then exam anxiety in step 2. So if you look up at the top of the model summary, you can see that when time spent studying is in the model by itself, the model explains about 15 or 16% of the variance in the outcome variable, and that's significantly better than a compact model that has no predictor variables in it. Then in step 2, or augmented model 2, where we add in exam anxiety, there's an improvement of about an additional 5% of the variance explained. So R squared goes up from about 15 or 16 to about 20 or 21, depending on how much you're rounding these things. That's a difference of about 0.05, and that difference, although small, is significantly different than no difference, and so we get a significance value that's less than 0.05, and we might interpret that as evidence that the model gets some significant improvement of fit when we add in exam anxiety. If we go down to coefficients, it's interesting to note that anxiety is a significant predictor in the augmented model, version 2, that is, the second augmented model step when it's added in. It's also interesting to note that revising or time spent studying, time spent revising isn't a significant predictor once anxiety enters the model. By itself in model 1, it is a significant predictor. You can see the significance level for the t-test associated with that one regression coefficient, the slope for time spent revising. It's significant in model 1, where time spent revising is by itself, but in model 2, once exam anxiety enters the model, it is no longer a significant predictor of the outcome variable. At this point, it's important to note that if our predictor variables are perfectly uncorrelated, that is, if they are orthogonal to each other, then the order that we enter them into our models, our augmented models, doesn't matter at all. This doesn't happen very much in non-experimental research, because often in psychology, most stuff we study is at least a little bit correlated with most other stuff we study. In some cases, in experiments, we can have orthogonal or perfectly uncorrelated predictor variables. We sometimes talk of different factors in an orthogonal design that we're maybe using an ANOVA to analyze. That's because a researcher can decide to randomly assign people to different levels of two predictor variables, such that your level on one predictor variable has no correlation or no relationship with your level on another predictor variable. Again, that happens, or that can be done sometimes in experiments. That's rarely the case outside of experiments. And so if we have a situation where our predictor variables are correlated, the order that they're entered into the model can matter, at least matter in terms of how we choose to interpret the contributions that each of those predictor variables make to the model. Just to put that another way, the interpretation of predictor variables can be different depending on which one gets to enter the model first. Which one becomes predictor variable 1 and which one enters second and becomes predictor variable 2. To try and illustrate what I mean, here's that first order that I ran, where anxiety entered first and time spent studying, revising, entered second. If we just look at the model summary here, and this is just the same model summary I showed you a couple slides back, you might make the interpretation based on these results that adding revising doesn't significantly improve the model. Most of the weight is being carried by exam anxiety. Most of the job of predicting is being done by exam anxiety. Yes, there's a really small improvement or increase in R squared, but it's not much, and it's not enough to be statistically significant. Using this same order, if we look down at those coefficients, we might again conclude that revising isn't really a very strong predictor of performance when it's in the model. So at step 2, or in augmented model 2, however we choose to describe it, we might conclude based on the results of these analyses that, gosh, time spent studying isn't doing very much. The standardized regression coefficient is a fair bit smaller for time spent studying than is the standardized regression coefficient for exam anxiety, and the standardized, in any case, the regression coefficient for time spent studying is not large enough to be significantly different from 0. The significance level is not below 0.05, so we might conclude time spent studying just isn't a very strong predictor in this model. Putting this together, we might make the interpretation that time spent studying isn't an important predictor of exam performance, which I don't know. Maybe that might strike us as odd. I mean, I think most of us as students, and certainly myself as an educator, would hope that time spent studying has some influence on how well you do or how poorly you do on a test. But the results of our analyses, when we run the model, the hierarchical model in this order, entering anxiety first and then revising, don't tend to suggest that it is. Now let's consider that second order, the one where we ran the hierarchical linear regression, we entered revising first and then anxiety. If we look at the model summary for that analysis, we can see that when it's by itself in model 1, that's augmented model version 1, time spent studying, revising, does significantly improve the fit of the model. That is, the fit of the augmented model relative to the compact model. The R-square is about 0.16. R-squared change, which is just change from 0, is 0.16. Those are always going to be the same values, and that's big enough to be statistically significant. We can also note that at step 2, or in augmented model version 2, when exam anxiety is added, there is a significant improvement in fit, but there's only a relatively modest increase in R-squared. R-squared goes from about from about 15 or 16% to about 20 or 21%, depending on how you round it, and that's an improvement of about 5%. That's not a lot. It is enough to be statistically significant, but it's a pretty modest improvement in fit. So if we look at the regression coefficients next, we notice maybe that in model 1, that's augmented model version 1, revising, time spent studying, is a significant predictor when it's in the model. When anxiety enters the model, revising is no longer a significant predictor of exam performance. Now, just for the sake of this example, let's assume that you weren't looking really closely and you missed this part. The point is, you might interpret the results, if you ran the model in this order, that time spent studying is an important predictor of exam performance. I mean, granted, this example sort of hinges on you not noticing that change in the significance level for the slope for exam, for time spent studying, but it still kind of illustrates, I hope, that you have basically the opposite conclusion if you run the model in the second order as compared to if you ran the model in the first order. And that may strike you as weird, or you might think, well, how does that happen? Why does this happen? Well, it happens because there's a lot of shared variance. There's a lot of overlap between exam performance, exam anxiety and exam performance. That is also shared variance between time spent studying and exam performance. If you think about that sort of checkered area in the middle, that's the problem. That's the area that's causing us this concern. And because of this shared variance, whichever predictor variable enters the model first gets to, in a sense, claim that shared variance for itself. And that means that there's less left over for the other predictor variable when it enters the model. So if exam anxiety enters first, it gobbles up or claims about 19% of the variance in the outcome variable, and that's enough to be a significant amount claimed, and we interpret that exam anxiety makes a significant contribution to prediction. If time spent studying enters first, it gobbles up or claims almost as much, about 16%, and we say, oh, time spent studying has this big value in terms of predicting the outcome variable. The important point here is when you're doing an analysis, a multiple regression, where there's more than one predictor variable, you really should think about those predictor variables, and at a kind of a conceptual level, ask yourself, how much do they overlap? You should also check how much they're correlated. I mean, this makes a really good case, I think, for understanding your data. Doing some simple bivariate correlations between all your different predictor variables, or indeed your predictor variable and your outcome variable. And if you noticed, as is the case in this data, that there's a pretty high correlation between time spent studying and exam anxiety. It's high in an absolute value. It's about, it's negative 0.71. That's big for psychology. You might wonder, like, gosh, this is potentially a problem. And it's a problem because when predictor variables are perfectly uncorrelated, like I described earlier, it sometimes happens in experimental designs. When they're perfectly uncorrelated, it's easy, relatively speaking, to interpret the contributions that each variable makes to the model and think about them, talk about them in terms of their relative strength as predictors. As I've said already, this is somewhat more common in experimental designs, and we sometimes, if you read textbooks about ANOVA, or if you read research methods textbooks about experiments, they'll talk about having orthogonal factors. These are just predictor variables, factors, that are uncorrelated with each other. They exist geometrically at right angles to one another. When predictor variables are somewhat correlated, and this is maybe a bit more common in non-experimental designs, it can become difficult to interpret their relative contribution to the model. You can still use them. You might have a model that includes 2 or more predictor variables, all of which are modestly correlated with each other, and that can be okay. But you can have a hard time if you want to really drill down and talk about the unique contributions, or kind of the incremental contributions of each of those predictor variables to the overall fit of the model, because those predictor variables are at least modestly correlated with each other. And it's even worse when predictor variables are really highly correlated with each other, because then it can essentially become impossible to talk about their unique contributions to the model or their relative strength. You know, if we have 2 variables that are really highly correlated, like let's imagine you're doing some sort of study where you are looking at exam performance and you're predicting it based on self-esteem and self-worth, which you're imagining are 2 separate constructs, but unsurprisingly are really highly correlated with each other. It's hard to talk about one as really all that distinct from another. A lot of what you measure with your measure of self-worth is also self-esteem, and vice versa. In those type of situations, or indeed in this example that I've given here, you might well consider dropping one of those variables because they're really highly redundant with one another. A lot of what you think is one is really the other, or vice versa. Or sometimes you can choose to make like a composite variable. So instead of having multiple predictor variables which are highly correlated, you take their average, or make a total score, or use some other calculation to create for each person a composite score that represents both of those otherwise highly correlated predictor variables. So again, the point of all this is you can do multiple regression in a hierarchical fashion, as I've described. However, if you do, you should make sure to think a little bit and to evaluate the extent to which your predictor variables are overlapping with each other, and how much of that overlap is shared with their relative overlaps with the outcome variable. Moving on now, after talking that point to death, or at least talking about it a lot, let's talk about different ways to do multiple regression that are program driven, where SPSS is essentially making a lot of the decisions for you. One of the options here is called forward, and this is where SPSS starts with a model that just has the intercept, just a simple compact model. Then it starts to add predictor variables in an order based on strength. It adds the one that has the highest correlation with the outcome variable, the one that's most correlated with the outcome variable, and if that regression is significant, that is, if that augmented model is better than the compact model, then that predictor variable stays in the augmented model, and then another predictor variable is added that has the highest semi-partial correlation with the outcome variable. And SPSS tests this new augmented model, augmented model version 2, and if it is significantly better than the first augmented model, it keeps this new predictor variable in the model, and so on and so on. Now, in our example here, we only have 2 predictor variables, but you could imagine if you had a situation where you had many predictor variables, SPSS would kind of sort of slowly, algorithmically sort of chunk through these different variables, adding one, then the other, till it gets to a point where the additional predictor variables aren't improving significantly the model's fit to the data, and then it would stop. It would have solved, or it would have found a model for you based on its selection of predictor variables. So it's going to keep on going until it can't add any more predictor variables, then it's going to stop and give you some output. Now, this particular example probably doesn't work all that well to describe forward selection for the model, because again, we only have 2 predictor variables, but since you've got the data set open, at least if you're following along with me, you've got it open, you can try this. All you really need to do is use the same regression module, except instead of having the method set on enter, which is the default, you pull the pull down menu and select forward. And you make sure that all your predictor variables are in one block, as they are here. So I put all my predictor variables, there are only 2 of them, in one block. I guess if you want, you could use other predictor variables like gender or major or class, if you want to sort of throw them in the mix. The critical part for the example is you select forward, and then you just go ahead and hit OK. And SPSS goes to work. I only included those 2 predictor variables in the model, and you can see what SPSS found is just one model. It picked the predictor variable that was most strongly related with the outcome variable, and that happened to be exam anxiety, and so it of course found one augmented model that looks just like the augmented model that we found earlier when we did this ourselves. It tried to add time spent studying, but that didn't improve the fit of the model, as we know already from our own experience, and it stopped. And so you can see our one and only augmented model includes only exam anxiety, and there's a little note at the bottom about excluded variables, which of course includes time spent studying. It did not go into the model. And there's some notes here about tolerance and collinearity statistics. I'm going to, for the moment, be silent on those because I actually get to those in my next lecture. So if you're wondering what those mean, like what's tolerance, what's collinearity, I'm totally going to be talking about those in my next lecture. SPSS also offers another option called stepwise. Stepwise is basically the same as forward, except it's got kind of a tweak or a twist. Every time a new predictor variable is added to the sort of developing augmented model, SPSS runs a removal test and potentially drops the weakest predictor. I don't know exactly what the criteria are for that test. I'm sure you can probably adjust them a little bit, but it essentially works, the stepwise essentially works like forward, but it can be a little bit more conservative, and it'll tend to, if it adds a new predictor variable, it'll sometimes drop a previously added predictor variable that now is relatively weak. But like forward, it's going to keep on going until it gets to the point where it just can't add any more predictor variables and get much of an additional improvement in fit. There's some other options as well, like backwards and remove. These are essentially the opposite of forward or stepwise. How they work is they begin with all the predictor variables and subtract them out. They kind of winnow away the weaker predictor variables, or kind of shave or trim away the weak predictor variables until they get to a point where removing variables doesn't improve the fit of the model. And if you want to try this, you can again go back to the regression module and use the backward approach. Just change method to backward and hit OK. And you'll see here, and just kind of what you would expect, SPSS begins with all the predictor variables. There are only 2 of them, exam anxiety and time spent studying, and then it removes time spent studying because time spent studying is a relatively weak predictor of the outcome variable, and it ends with model number 2, which is a smaller model, a smaller augmented model that has just exam anxiety. So you kind of end up in the same place, except rather than adding predictor variables, you're subtracting predictor variables. So as I like to think of it, there are essentially 2 different ways to do hierarchical regression. To do multiple regressions in SPSS. There are the ways that are researcher driven, like forced entry or hierarchical, where you as the researcher, as the data analyst, are making the decisions. And there are also various program driven or computer driven approaches where SPSS is either adding or removing predictor variables until it finds a solution that in a sense it likes. I note here that these are doable. I mean, you certainly can use them, but I think they're best left for exploratory research where you don't really have a strong theory that you're trying to evaluate. You're not testing particular hypotheses. If you have a particular hypothesis, a researcher-driven approach probably makes a lot more sense. And there is some danger with computer-driven approaches or program-driven approaches like the ones offered here. If you have a situation where you've got a lot of predictor variables and some of them are quite redundant or highly correlated with each other, because you can end up in weird positions where SPSS will find a model that is maybe overfit to the data, meaning it fits the data in the sample very well but might not fit the data in the population all that well. Or you can have problems with a phenomenon called suppression, where predictor variables behave rather differently depending on the presence or absence of other predictor variables in the model. And suppression is a bit of a weird topic. I've actually done a whole separate supplemental lecture on it, so if you're really intrigued, by all means check it out. I mean, I think I do a decent job explaining it. Suppression effects are not impossible in other ways of doing regression analysis, but they seem to be at least potentially a problem, more so if you're doing a kind of a computer-driven approach where you're not really paying a lot of attention and just allowing SPSS to make the decisions for you. I always think it's best to make your own decisions if at all possible. And more to the point, your decisions about adding predictor variables to the model should be very much based, as I've said earlier, on theory, that is, on the research, or on the theory that informs your research, your area of interest, or based on previous research or clinical experience in that area. You should be thoughtful, mindful about the type of variables that go into your model. Model building, that is, finding the augmented model that fits the data the best, is really ultimately this balancing act I've talked about before. It's a balancing act between explanatory power and parsimony. Adding predictor variables to a model improves explanatory power. R squared gets bigger, if only by a little, hopefully by more than a little bit. There's almost always a little bit of an R squared change. But there's also a decrease in parsimony. Adding predictor variables to a model makes the model more complex. It makes it less simple. And we tend to like simple. We want models which have as few variables or few predictor variables as possible. We want to find that sweet balance where we've explained quite a lot of variance in the outcome variable using as few predictor variables as possible. Adding too many predictor variables usually ends up in a place of diminishing returns, where each additional predictor variable gives only a very small increase in explanatory power, and there's relatives to it, its big decrease in parsimony. And like I said before, there are sort of fussy and particular problems like overfitting and suppression, which can also occur. They're probably a little bit more problematic if you're using program-driven approaches to variable selection. And as I noted before, I have a whole supplemental lecture that talks about this, so I won't do a lot of talking about it right now. Alright, so a lot of talking. Now I want to transition and do a practice problem. If you're enrolled in my class, you can download the data and play along with me. Imagine that you're a clinical psychologist who's studying drinking behavior, alcohol use, and you're doing a non-experimental design where you have a predictor variable that is a measure of the drinking to cope motivation. This is one of the motivations that people have for using alcohol. It can be measured on the drinking motivations questionnaire. People who score highly on this measure tend to drink as a way of self-medicating, of dealing with life's adversities. People who score low on this measure tend to not do that. It's a variable that's associated with drinking problems. If you tend to drink in response to problems, down the line you tend to have more problems, perhaps unsurprisingly. Let's imagine your other predictor variable is gender, and your outcome variable is a measure of drinking problems, like things like number of times that you are hungover or sick or miss work or get into fights or get in trouble with the law. There are many measures that try to quantify the sort of the incidence and the intensity of drinking problems, and let's just assume for this example you have one of those. So you gathered people using an online survey or an in-person survey. You asked them to fill out a drinking motivations questionnaire to get that drinking to cope measure. You asked them to identify their gender, and then you asked them to fill out a questionnaire that has to do with alcohol problems, that gives you the alcohol related problems measure. By the way, if you're not enrolled in my class, and if you're just highly motivated to follow along with this example, and if so, good for you. Here's the data. I just did a little screenshot of the SPSS file I'm working with. This is data that I made up myself. You can see I have 28 people here, a measure for problems, a measure for the coping motivation, and then a variable to code male or female gender. So if you want, you can just copy this into SPSS and kind of play along with me. So if we want to represent this study pictographically, we can think of our two predictor variables being coping and gender, and our one outcome variable being alcohol-related problems. Let's imagine we want to do a hierarchical regression, and in step one we enter coping. That's going to be our coping-related variable. And in step two, we enter gender. And let's assume we have a good reason for doing this. Perhaps we have a hypothesis that gender contributes to alcohol problems after controlling for drinking motivations. This is, I think, the way people often use multiple regression. They say, does a particular predictor variable contribute to the outcome variable above and beyond some other well-established predictor variable? We've also already established that the drinking to cope motivation is related to alcohol problems. That's not really new, but we might have a question as to whether gender is related to alcohol-related problems after we've controlled for this other predictor variable. So if you're working on this with the data set from Blackboard, or if you've taken the time to quickly copy that data into SPSS, go ahead and run a multiple regression now using these steps. And while you're at it, do some regression diagnostics. Look for outliers, extreme values in the raw data, and extreme values in the residuals that could indicate problems with our data set. Let's also look for some influential cases that pull the model more than they really should and make the model fit the rest of the data poorly. And these are called regression diagnostics, but like I've said before, I think these diagnostic steps should be done almost always when we're doing any sort of analysis like the one we're doing right now. So you're either working on this, or maybe you're just watching the video to follow along. If you were just following along, here are the steps that I did. Obviously, I opened up the regression module. My outcome variable is alcohol-related problems. In block 1, I entered drinking to cope motivation, and in block 2, I entered gender. Then, before hitting OK, I asked for some, I asked SPSS to save some values for the unstandardized and standardized residuals, some influence statistics like DF betas and standardized DF betas, DF fits and standardized DF fits, the predicted values, unstandardized and standardized versions, some measures of influence, Cook's number and leverage values, and so on. I also asked for plots. I asked for a histogram and normal probability plot for my residuals, and I also asked for one of the many different sorts of regression plots you could make. I'm here predicting on the y-axis standardized residuals, and on the x-axis I'm just putting the dependent variable. So I could put, like, dependent variable, I might put predicted or standardized predicted value on the x-axis. I just want to see if those errors, those residuals kind of spread out or bunch up at different points in my prediction. So here's some of the output I get. It looks like our outcome, our model, that is the augmented model, model A, is significant at each step. Adding coping motivations significantly improves the fit of the model as compared to the compact model, and then adding gender additionally improves the model. So we go up from about 40% variance to about 60% variance explained. Both of those steps are statistically significant. And if we look at drinking to cope motivation, you may notice here it's a little bit like the earlier example I gave you, where drinking to cope motivation looks like it's statistically significant at the first step, becomes non-significant at the second step when gender has entered the model. This is maybe a little bit of a clue that there's an interesting relationship between our two predictor variables. And because this is fake data that I kind of contrived, there is a little bit of a story there as to why the predictor variables drinking to cope motivation and gender are not uncorrelated with each other. So anyway, at this stage, if we were going to interpret the results, we might say, well, gender contributes to alcohol problems when coping motivations are controlled for. That's a reasonable interpretation. We could also say coping motivations don't contribute to problems when gender has entered the model, and that's pretty weird given the literature on the drinking to cope motivation. We'll kind of get to that a little bit later. But before we do, let's think about those regression diagnostics. First, we might look to see, are there any outliers? And maybe we can wonder, if so, what do we do about them? And then, of course, are there any influential cases? What do we do about those? Again, when I'm thinking about regression diagnostics, I think about these two broad areas of concern. One is outliers, and the other is influential cases. So with respect to outliers, we can consider outliers in terms of the raw data for our predictor variables, our outcome variables. We can also consider outliers in terms of residuals, and this is arguably more important because we're a little bit more concerned about the residuals for our model than the raw data itself. Although, to be fair, we should look at the raw data as well. So first, let's consider the raw data. Let's look for outliers and consider the shape of the distribution for our predictor variable alcohol problems. Our predictor variable drinking to cope motivation and our outcome variable alcohol problems. Now, our other predictor variable gender, we're not going to include in these kind of analyses because this doesn't have much of a distribution. It's either value, the codes I think are 0 and 1 for male and female respectively. I mean, if this was a real example, we would want to look at that data to see if there are any impossible values. If the values for gender can be either 0 and 1 and we see somewhere there like a 10, then clearly that's a data entry error. But assuming we've already done that kind of cursory inspection, let's just look at the distributions for our continuous variables. And I'm using the Explorer menu just because I find it's a nice almost one-stop shop for this type of work. So analyze descriptive Explorer. I'm entering on my dependent list our two variables that we're interested in. In the statistics area, I'm clicking on the statistics button, I'm asking for outliers. And in the plots area, clicking on the plots button, I'm asking for those normality plots with tests. I could ask for some other stuff like a histogram, but I'm actually not going to bother with that. If this was a real analysis, I would, because I like making graphs, but I'm not for the sake of efficiency right now. If I look at my descriptive statistics for my predictor and outcome variable, I can look at the means and standard deviations and kind of eyeball the range of values and see if I have lots of values that fall outside of 2 or 3 standard deviations above and below the mean. I can also look at the extreme values, the outliers, if I've asked for that, which are the 5 highest and 5 lowest cases on each of those variables. And here, there's not a lot of evidence for outliers. I don't see a lot of cases which are higher than 2 or 3 standard deviations above the mean or below 2 or 3 standard deviations below the mean on either of these two variables. If I'm interested in the shape of the distribution, I could get those normality plots. I think I haven't shown them in this PowerPoint, but I should have them somewhere. I also get my normality tests, the Kolmogorov-Smirnov test and the Shapiro-Wilks test. These are significant for alcohol problems, which suggests that the distribution of values for alcohol problems is significantly different from a normal distribution. That's probably not too bothersome for 2 reasons. One, and maybe most importantly, we don't assume that our raw data is, or our sample data is, normally distributed. It's often nice if it is, but it doesn't have to be. And in the case of alcohol problems, we might not expect a normal distribution. We might expect a skewed distribution, such that most people in our data set have few or no alcohol problems, thankfully I suppose, and a very small number of them have a lot of alcohol problems. So the data probably is quite positively skewed, with most of the values being around 0 and a few of them being rather high. So the fact that our normality test isn't particularly, isn't picking up or is suggesting non-normality shouldn't bother us too much. And I've also included that caveat that these tests tend to be really underpowered anyway, so it's probably not worth looking at them too awful much. But because I've done them, just to highlight here, both of these tests are significant, meaning that those distributions, or I should say that distribution for alcohol problems is significantly different from normal. Now maybe a bigger concern, or more important concern, is looking at our residuals and looking at their distribution. So again, using the Explorer module, I'm doing the same thing I did before, except instead of looking at the sample data or the raw data, I'm now looking at the unstandardized and standardized residuals. To be clear, I don't need both of these. I'm just doing both of them. Probably just do the standardized one. They have the same distribution. Anyway, with those in my dependent list, I'm again asking for normality plots and tests, and I'm again looking at outliers. And again, looking at the descriptive statistics, it's pretty clear there aren't any obvious outliers with respect to residuals. The lowest and highest values are well within what we'd expect from a normal distribution. I'm not seeing standardized values for our residuals that are greater than 2.5 or less than negative 2.5. There's one case there, but he or she is 1 out of 20 or 30 people, I think, so that's not entirely unusual. If I saw lots and lots of values with standardized residuals of 2s and 3s and 4s, I'd be really worried. That doesn't appear to be the case now. If I look at those tests of normality, I see that our residuals are not, the tests are not significant, meaning that the residuals are normally distributed, which is good, because we assume that our residuals are normally distributed. That's an assumption we make for regression analysis, and if we didn't see that, we'd worry a little bit about how robust the results of our analysis would be, or to put it another way, we'd worry about bias. Anyway, just to be clear here, I don't need to run these tests on both the standardized and unstandardized values. As you can see, the results are the same because, of course, the distributions for unstandardized and standardized residuals are the same. So we've looked at our outliers, both the data, sample data, and the residuals, and there are no apparent problems. Well, that's good. Now let's consider influence. And remember, we can think about influence in two different ways. One is the influence on the prediction of that one case, how much that particular case pulls or distorts the model's prediction of it. And to think about that, we often focus on the adjusted predicted values and the deleted residuals, either unstandardized or studentized, studentized being a way of standardizing. Also think about influence in terms of how much a case influences the prediction of all the other cases in the data set. Here we have things like Cook's distance, leverage values, DF betas, and DF fits in their various sorts. Now, my analyses already asked for those influence statistics, so all I'm going to do now is look for high and low values. And I'm just using the sort function here, data sort cases. I'm sorting descending by both Cook's distance and leverage values, just to put the highest values at the top. And here there's one case who happens to have very, relatively speaking, large values for these measures of Cook's and leverage, especially Cook's distance, and also for some of the other regression diagnostics. So we can see if we look at the residuals and the predicted values and the residuals and the standardized predicted values and the residuals, here's that one case that had that outlier that was a little bit big. In and of itself, that's not a huge problem, but it's interesting that that one case was our kind of outlying with respect to residuals case. It's also worth noting that that's a case which has a lot of influence in terms of how the model predicts all the other cases in the data set. So, I mean, this is fake data. I kind of engineered it to have this problem, but we have this interesting case where our one potential outlier is also an influential case. It's not always going to be the case that outliers are influential or the influential cases are outliers, but it is sometimes that way, or it is sometimes that case. And here it is. Our outlier with respect to residuals is also a fairly influential case. If we want an illustration of that, we can just make a scatter plot. We have two predictor variables. Why don't we do this? We're going to do a scatter plot, and we're just going to make a straight, simple scatter plot by dragging that into the workspace. I'm putting drinking to cope motivation on the x-axis and alcohol problems, of course, on the y-axis. I get my scatter plot that looks like this. I use the little bullseye tool to highlight the case that is outlying. It happens to be case number 1. Case number 1 because remember, I sorted the cases descending in terms of influence statistics. So case number 1 is going to be at the top. I don't know off the top of my head what the ID number for that person is. Oh wait, yes I do. It's ID number 3. So that's our weird case. Now we might well ask, how well would the model work if we didn't have this case, if person number 3 wasn't in the data set? And we can actually test that little hypothesis, or we can answer that little question, I guess I should say, by using select case. Let's go to data, select case, and set up a condition. Select case if a particular condition is satisfied, that condition being ID number is not equal to 3. I hit continue. I hit OK, and it filters all the cases. I'm just going to go ahead and make that scatter plot again. You can see the scatter plot looks a little bit more regular. You've got nice distribution of residuals. It looks like it's pretty even in variability, and it's not all bunched up in one area. If you slide backwards a little bit, you'll notice the R squared for the model used to be about 0.40. Now it's 0.68, which is ridiculously high. This is fake data that I made up. For the sake of house cleaning, I'm just going to go ahead and delete these old regression diagnostics because I'm about to run the analysis again. So now I'm going to run the analysis again. The difference now is I've filtered out ID number 3, and I'm using the same hierarchical ordering that I did before. I've got alcohol, drinking to cope motivation going in step 1 and gender going in step 2. And now model A is significant only at the first step. Drinking to cope motivation is significant, significantly improves the fit of the model. At step 2, the addition of gender adds only a very small amount of additional variance, about 4% variance explained, and that's not enough to be a significant improvement. If we look at our model now, drinking to cope motivation is significant at both steps, and gender, again, doesn't really contribute to the model. So now if we're going to try and interpret the results of this regression, we might say, well, there's no evidence that gender contributes to the alcohol problems when drinking to cope motivations are controlled. But to get this finding, to get this cleaner result, we had to use our regression diagnostics. We had to be a little bit careful and explore the data. And a couple things here. One, let's assume we have a good reason for excluding ID number 3 beyond just that he or she is an outlier, a potentially influential one. Maybe we found some laboratory notes that justify the exclusion of this person, so we can kind of back it up and not just cherry pick our data. Also, let's be clear, when I'm saying no evidence, especially in a small sample like this with relatively low statistical power, absence of evidence isn't evidence of absence. We need a good solid design and high statistical power to interpret this null finding, to say that technically gender has no effect on alcohol problems once you've controlled for drinking to cope motivation. All we can say here is not that there is no effect, rather we have no evidence of an effect. Absence of evidence isn't evidence of absence in a low-powered, non-experimental design like this. Anyway, wow, coming into over an hour again. This is a marathon, so if you made it this far, thanks for your attention. You may be thinking, wait a sec, we've talked all about multiple regressions, well, simple regression, multiple regression. We haven't really talked a lot about how to interpret those regression coefficients, or really what they mean, especially in the context of multiple regression. Why not? Well, the why not is, I'm going to do it in my next lecture. Interpreting regression coefficients in the context of multiple regression can be a little bit tricky, and it depends a lot on whether we allow our predictor variables to interact with each other, which brings us into the world of interactive models, which I really like to talk about, and I'm really looking forward to talking about. And that's what we're going to start talking about or looking at next time. So until then, take a break, take a rest. This is a peaceful cherry blossoms to hopefully inspire you to relax a little bit and let this stuff sink in that you've been thinking about or listening to. I hope it's made sense. If it hasn't, please let me know. Hit me up on YouTube with a comment in the comments area or a question. If you're enrolled in my class, please ask me a question in class or email me a question. I do want to explain this to you in a way that you understand, and if I'm not doing that, then please let me know and I'll try to do better. Remember, learning statistics is this sometimes Sisyphusian, at least Sisyphusian seeming task, where we struggle and fail and struggle some more, and eventually we gain some sort of, if not mastery, some sort of existential transcendence through the whole process. And after all these years, I think that's mostly what I'm looking for. Anyway, on that weird note, let's conclude. I'll catch you next time. Bye-bye.